Welcome to today's lecture on necessary and sufficient conditions for a quadratic form to follow a chi-square distribution. This is a part of our multivariate analysis series. I am Dr. K. Manoj, Assistant Professor of Statistics at Manonmaniam Sundaranar University. Quadratic forms may sound abstract, but they appear everywhere in statistics. For example, in calculating sample variance, in regression, and ANOVA, sums of squares, and in advanced multivariate tests like Hotelling t-square and MANOVA. So, it is essential to know when a quadratic form behaves like a chi-square distribution. A quadratic form is an expression of the type Q equals x prime ax. Here, x is a random vector and A is a symmetric matrix. Many of our familiar sums of squares can be written in this form. Remember that if the sequence of z1, z2, zk are independent standard normal variables, then their sum of squares follows a chi-square distribution with k degrees of freedom. This is the structure we want two quadratic forms to take. When x follows a multivariate normal distribution, the distribution of q equals x prime ax depends on the eigenvalues of matrix A. Not every quadratic form is chi-square. The matrix A must satisfy specific properties. For a quadratic form to be chi-square distributed, three conditions must hold. The random vector x follows a multivariate standard normal. The matrix A is symmetric and idempotent. The rank of A equals the degrees of freedom k. Idempotency means A square equal to A. Such a matrix acts like a projection. It projects x onto a subspace of dimension k. The quadratic form then reduces to a sum of k squared normals, exactly a chi-square distribution. Take the sample variance of normal data. It can be expressed as a quadratic form, and when standardized, n-1 s square divided by sigma square follows a chi-square distribution with n-1 degrees of freedom. Here, the rank of the projection matrix is n-1, which explains the degrees of freedom. In regression, the regression sum of squares, or SSR, is y prime py, where p is the projection matrix onto the column space of the predictors, because p is idempotent and has a rank equal to the number of predictors. SSR divided by variance follows a chi-square distribution. This forms the basis of ANOVA and F tests. Moving to multivariate test, Hotelling's t-square statistic is also a quadratic form. Under the null hypothesis, it reduces to the chi-square distribution, or equivalently a scaled F distribution. This connects quadratic forms directly to multivariate hypothesis testing. To summarize, a quadratic form Q equals x prime ax follows a chi-square distribution if x is standard normal, A is symmetric and idempotent, and the rank of A equals the degrees of freedom. These results underlies sample variance, regression, and ANOVA and multivariate tests. Here is the geometry. Vector x is projected onto a subspace. The length of this projection is captured by x prime ax. That length squared corresponds to a chi-square variable when the conditions are satisfied. Breaking x into independent standard normal components, the quadratic form becomes a sum of squares coordinates. This is precisely how the chi-square distribution arises. In regression, the observed vector y is projected onto the fitted values. The quadratic form y prime py measures the variation explained by predictors, and its chi-square distribution allows us to perform hypothesis testing. Thank you for watching. If you found this useful, like, share, and subscribe for more lectures on statistics. Please leave your questions in the comments, and I will be happy to respond.